Hi everyone, welcome to Integral Calculus. Today we explore lesson 6.4, work to pump out liquid. Number 1, intro. Every liquid has a mass. And from physics, we know that force is mass times acceleration, where mass is volume times density. Work is force times distance. When we do the substitution for force, we get mass times acceleration. Do the substitution for mass, we get volume times density. So work is volume times density times acceleration times distance. If unit is in joule, if the unit is in foot-power, then we have work to be volume times density times distance. The mass density is denoted as rho, unit kilogram per cubic meter. Weight density is denoted as delta, unit pound per cubic foot. The gravitational acceleration is denoted as G, where G is 9.8 meter per second square. Let's take a look at some example. In the first example, how much work is needed to pump all the water out of a cylindrical tank with a height of 10 meters and a radius of 5 meters? The water is pumped to an outflow pipe 15 meters above the bottom of the tank. The density of water is 1,000 kilograms per cubic meter. Let's sketch out a picture here. This is the cylindrical tank. It has a height of 10 meters. And it has a radius of 5 meters. The outflow pipe go from the bottom to the top, 15 meters. Notice that the force to pump out each slide of water is different. And so in order to calculate the work, we need to use integration. Let's compute the work done to pump, move, or lift a sample slide. So this is what a sample slides look like. Okay. And we're gonna compute the work to pump out a sample slide. Work is volume times density times acceleration times distance. The volume of the sample slide is pi r squared, and then multiply to the thickness dy. If we set this to be the y-axis, so this number down here is gonna be 0. Up here is 15. Density, well, 1,000 kilograms. Acceleration, 9.8. Distance, the distance from 0 up to the sample size y. So that means the distance required to pump out the sample slide is this distance, 15 minus y. Yay! Next step is, well, we know the radius is 5. So we can sub the radius 5 in here. 5 squared. And we have the work to pump out a sample size. Let's just simplify this a little bit here. It is the 9.8 times 25,000 pi 15 minus y dy. Then the work to pump out all the water is going to be, well, we're going to pump out all the slides from 0 up to 10 because the cylinder has a height of 10 meters. Integral from 0 to 10 of the work to pump out a sample slide 9.8. It's not 25,000 pi 15 minus y dy, and this would be a 9.8 25,000 pi 15y minus y squared over 2. Evaluate from 0 to 10. So we have 9.8 times 25,000 pi 15 times 10 is 150 minus 10 squared is 100 divided by 2 is 50. And then when we plug in 0, we get 0. We can plug this in the calculator and get a nice number. And that number is the approximately 77 million joule. Oh, is the big number. Let's take a look at the second one. In example 2, an aquarium 2 meters long, 1 meter wide, and 1 meter deep is full of water. By the work needed to pump half of the water out of the aquarium. It is the sketch of an aquarium. Let's sketch a sample slice. This is the sample slice right here. We're gonna figure out how to lift or pump this sample slice out. The work to pump out a sample slice is the same formula. Work is the volume times density times acceleration times distance. Sample slice just a rectangle. So I mean the volume is the base area times the thickness. If you look at the base area here, there's length and width. 2 times 1. The thickness is dy. Density 1,000. Acceleration 9.8. The distance, okay, same thing. If we use the y-axis, then this distance is y, and the distance that is requiring to move a sample slice of water is 1 minus y. Simplify this and we have a 9.8 times 2,000. Multiply to 1 minus y dy. Next step is we're going to set up the integral to compute the work. the work is gonna be, well, we're gonna have to pump half of the water out. So in order to get half of the water out, we're gonna pump the top half. Integral from 0.5 to 1 of 9.8 times 2000 times 1 minus y dy. We have a 9.8 times 2000 y minus y squared over 2, 0.5 to 1. 9.8 times 2000, do the substitution. 1 minus 1 over 2 minus 0.5 minus 0.5 squared over 2. Use the calculator. And we have 2450 joule. Very nice. Okay. Let's take a look at another one. In exercise number 3, a spherical tank of radius 4 meters is half full of liquid having density 900 kilogram per cubic meter. Set up an integral to compute the work done in pumping out the remaining liquid through an outflow pipe located at the top of the tank with length 1 meter. Let's just sketch it out. So here comes a sphere. Yeah. And then up here, there's an outflow pipe. Do this sketch, it is better. With this, haha. Outflow pipe, 1 meter. The sphere has the radius of 4 meters. So I mean, the distance from here to here is 4. And this distance is also 4. It's only half full, meaning that all the liquid is going to be down here. So in order to pump out all the liquid, we're going to take a look at the work done to pump a sample slide. Sketch our sample slide. This is the sample slide here. Work to pump our sample slides, same formula. Volume times density times acceleration times distance. Okay. The volume is the base area times thickness. So that would be, the base area is the pi r square. Thickness here is, well, we can put the y-axis like this. I'm gonna make this the y-axis right here. And this would be the x-axis. So I mean, this is the radius r. And the radius r is exactly x. we can figure out the radius because we know if you look at this, the circle of radius 4, so circle of radius 4 centered at origin, x squared plus y squared equal 4 squared. So we know that x squared is 16 minus y squared. Oh, volume is pi r squared, so it's the same as pi x squared. Time, the thickness, that is the base area, thickness is dy. And because we know the radius is x, so we can do the substitution here. It's pi 16 minus y squared. dy. Density 900, acceleration 9.8. Here comes the distance. We have to pump it a distance of this one right here, y. And also this distance, this is the distance of 5. So together, the distance is 5 minus y because y is below the x-axis, so it is negative. 5 minus y. Reason why we do this because the y is below x-axis. Yeah. Simplify this and we're gonna have a 9.8 times 900 pi 16 minus y squared times 5 minus y dy. Now the work to pump the bottom half is, well, we got to lift up each slide from -4 to 0. As you see, and the y value is negative, which is why the distance is 5 minus y. 9.8, 900 pi multiply to 16 minus y squared, 5 minus y dy. That is it. That is the setup right here. One more. In the last one, we have an isosceles triangle water trough, has a height of 3 feet and a base of 3 feet, a length of 10 feet. Set up an integral to find the work required to pump all the water out through an outlet pipe 2 feet at the top of the trough. Water has density 2.5 pounds per cubic feet. This is the picture of the isosceles triangular water trough. In order to pump all the water out, we got to take a look at how we're gonna pump a sample slide. Let's sketch out a sample slide. Oh, sample slide is just a a rectangular box. Use the same formula. Work to perm out a sample size is volume times density times acceleration times distance. Let's take a look at the volume here. The volume of the sample size is the base area times thickness. Well, the base area is the length times width. So we know the length is 10, but then we don't know the width. That is extra here. We need to figure out that x. So 10x, the thickness is. We can use the y-axis. So this would be the y-axis right here. And it's going from 0 up to this is the y-axis. Okay. Thickness is dy. To figure out x, right? Notice that there are two triangles, the smaller one and the bigger one. Two isosceles triangle. So for the smaller one, it would be x over. Well, this distance right here is y, because we use the y-axis. Use similar triangle. X over y equal, well, the similar ratio for the bigger isosceles triangle, 3 over 3. So I mean x equal y. Oh, how nice. And times x, and in this case, yeah, it is just y. And y dy density is 62.5. Well, we don't have the acceleration here because the unit of density is in power per cubic feet. So no acceleration. It's just time distance. And the distance here is from the border to the sample slice is the distance of y. So from the slide all the way up to the outlet pi, because I minus y. Simplify this and we have a 25 y times 5 minus y dy. Yay, that is the work to perm our sample slice. So the work to perm out all the water is, just got to add up the sample slice from the bottom to the top. So that is from 0 to 3 because the height is only 3 feet. 25 y 5 minus y dy. And this is it. Thank you for watching. I hope you found the content useful. Please like, subscribe to help the channel grow. I will see you in the next video.